Okay, so probably nothing super exciting today, but yesterday we talked about area between curves and we didn't do any examples, so we probably should. Example, find the area between, this is some input delay. Find the area between, we can keep our first example relatively simple. F of x equals x, g of x equals x squared on the interval from 0 to 3. So our formula for area, if we've got an upper function and we've got a lower function, then we need to integrate the upper minus the lower. And of course, to do that, you need to know which is which. So, I mean, you might just sort of be able to figure that out. But this is why I brought Desmos up. Let me share this so it's showing up in the recording. So here's x, and here's x squared, and this is actually maybe a kind of wonky choice as an initial example. I'm just using my notes from last year, but the reason I say this is kind of a wonky choice is that the upper and the lower function aren't constant, they switch. So here, x is the upper function, and here, x squared is the upper function. So if you ask what's the upper minus the lower, it's a little complicated. Let me do this problem, but maybe let me not do it immediately. Let me do an example first where there isn't any complication like that. Let's just do an example where one of the functions is always less than the other. So it's this one, it is. Okay, let's go ahead and use these for our first example. E of x and 1 minus x. And the area between them, let me see if I can get Desmos to generate this. The area between them from, let's say, 0 to 1. So we've got a single upper function that never changes, and we've got a single lower function that never changes, and the area between them are going to find via integration. So let me see, the exponential was the bigger. Did I say from 0 to 1? So the exponential was the bigger one. So the upper minus the lower. We need to be careful not to make any sort of algebra mistakes. We're subtracting g of x, so we're subtracting 1 minus x. And that negative sign distributes and turns into this. And this is a pretty, using sort of words like straightforward is always dangerous because maybe it's not straightforward if this is new to you, but when I say it's straightforward, I just mean we don't have to use U substitution or any kind of tricks to take this integral. The antiderivative of e to the x is e to the x. The antiderivative of -1 is what?
Negative x.
The derivative of -1 is 0. The antiderivative is x, or negative x, I should say. And then the antiderivative of x squared, or rather of x. This is a power function. You bump the power up, and then you divide by it. And there's what we get when we plug 1 in, and when we plug 0 in, a lot of stuff goes away, but e to the 0 is 1. So this is, we've got an e, we've got a -1 and a +1/2, so that's a -1/2. And then we've got a -1. So that's a -3/2. And I could go to a calculator and get the decimal if I wanted to. I mean, my normal sort of philosophy is that in word problems and applied problems, you need decimals because you can't, tell a store that you want to order E -3/2 gallons of paint, but for just a completely abstract math problem like this, that's probably fine. And I mean, we can make examples worse in the sense that we can make examples that require U substitution, but so that I don't forget, let's go back to this. We're not going to need any fancy integration techniques here, but we are going to have to think what to do. And again, if we go back to Desmos, let's see, I have to share everything because I'm recording this. It won't show up if I don't. If we go back to Desmos and we look at x and we look at x squared, and we're looking at both of these on intervals from 0 to 3. Has everyone here used Desmos, by the way? It's a very useful tool, much nicer graphs than you get messing around with your calculator. So let's see, let's not zoom out, but let's push up this Y maximum so we can see both graphs in their entirety. So as I said earlier, there isn't an upper graph and there isn't a lower graph. Or rather, which curve is the upper curve and which curve is the lower curve changes. So a situation like this is just going to require a little more work. But I mean, how might we approach this?
Separate it into two problems.
Separate it into two problems is exactly correct. So we look at, they intersect here, they intersect at 1. So if we look at this from 0 to 1, we have an upper curve and a lower curve, and we can take this integral. And then if we look at these from 1 to 3, we have a lower curve and an upper curve, and we can take this integral. So formally, we're using a rule of, well, of integration, I guess you could say, which says that, you can chop an integral up. I mean, if you think of an integral as an area under a curve, or in this case, an area between curves, you can look at separate areas separately and then just add them up. Now, let me go back to Desmos and say something more. Let's look at the whole thing now. Notice that, this place where I'm chopping it up, as it were, is this point of intersection between the curves. I mean, how can this curve stop being less and start being more than this other curve? Well, by passing through it. So in situations like this, the sort of chop points are going to be where the curves intersect. And I mean, finding where curves intersect is a matter of setting them equal to each other. And whether that's easy or difficult or somewhere in between is going to vary from problem by problem. And honestly, my advice is, some people would not like this, but my advice is to use technology to find any intersects you need. I mean, you're trying to do a calculus problem. You don't want that to turn into some kind of 3-page algebra exercise. Here we wouldn't need 3 pages, but if you're, I mean, I don't really mind if you did not want to share that. I'm all for just using Desmos. I'm all for sort of open source solutions, but let's just real quick go to our calculator. And let's say we were doing this on our calculator. And we looked at the graph and we kind of see your calculator, as we're seeing, is not as nice as Desmos, but also for some reason we had a wonky viewing window. Let me try to make this a little more habitable. Maybe zoom standard. Okay, you cannot see anything. Let's try this again. I don't actually like using Zoom except for Zoom standard. It's, I guess, a personal thing. I just like messing around with windows. I can see, I don't know if you can see from the back of the room, but if you're close to this, you can see, and also if you're not colorblind, probably, you can see that the blue curve is greater up here, and then you can see that the blue curve is less over here. So there must be some kind of point of intersection around here. It's hard to make out, but maybe if we go from -1 to 0 to 3 or so. And then, my goodness, I don't know what is with technology this week. But if we're very patient, we can do that. And now we can sort of see this. And if you're on Desmos, you know, you didn't need anything fancy. When I wanted to know where the intersection was on Desmos, I just sort of clicked around here, and Desmos figured out for itself that that was what I was looking for. On your calculator, there's a command you can use. Hiding, I believe, in the calculate menu up here. If we press second trace, there we are. There's a curve intersection feature, and we tell it, you see, we can move between curves using the up and the down arrows, and we tell it by clicking entry, it's asking what our first curve is. We press enter. Second curve, I guess we don't have, I guess it switches curves automatically. We press enter again. And then it's asking for a guess, because you see there can be multiple points of intersection. In fact, that's happening here. There's a point here at 0, and then there's this point that we're actually looking for. So we use these left and right arrow keys to get kind of near the intersection point that we're looking for. Hopefully that's close enough, and we press enter, and there's how we would do that on our calculator. Or significantly faster on a physical calculator where you're not fighting the technology. So now, that's shared the wrong thing there, I guess. So now let's solve this. So here are our curves. We've got this region between 0 and 1, where the linear expression is greater than the quadratic. And then we've got this area from 1 to 2, where the quadratic is greater than the linear. And we take this piece by piece. Oh. Might have to figure out another solution if Zoom doesn't start behaving a little better. But that first integral, our upper curve is the x. Our lower curve is the x squared. And then that second region, not 0. The lower curve is 1 and the upper curve is 3. I mean, the lower limit of integration is 1 and the upper limit of integration is 3. As far as the curves, upper minus lower. And we don't have room on this frame, but neither of these integrals requires anything fancy. There's no U substitution or anything like that. We've got a power function minus another power function. To find the antiderivative, we bump the power up by 1. And then we divide by that new power. Bump the 2 up by 1, it becomes 3. Divide by that new power. We're integrating from 0 to 1. Really, a lot of times, this is my sort of the most tedious part of the problem. Like if you've got like 7 terms, you've got to stick 14 things into your calculator when you do the subtraction. But here things work out nice. You stick 1 in, you get 1/2 minus 1/3. You stick 0 in, you get 0. Let's see, 1/2 minus 1/3, 3/6 minus 2/6 is 1/6. And then we, of course, have not finished the problem. We found part of the answer. We found that area there. To find the rest of the answer, we take the second integral, 1 to 3. X squared minus x dx, the antiderivatives we take. I'm going to say that if you struggle to take these antiderivatives, this is something you should be drilling aggressively. We should be able to take antiderivatives of power functions without a lot of hassle. And now going back to what I said earlier, the really, to me, tedious part of this problem is, let's see, we stick 3 in there. We get 27/3 minus 9/2. 3 squared is 9 over 2 minus 1/3 minus 1/2. And then whatever this is, we take it and we add 1/6, and there's the answer. And honestly, this might be easiest to just quickly go to our calculator. So we've got 27/3 minus 9/2 minus 1/3 minus 1/2 plus that 1/6. And our, or at least under ordinary circumstances where you're not, oh, our calculator suddenly decided it wants to work, not would. 27/3 minus, our calculator will do the correct order of operations. We don't need parentheses there. Minus, we don't need parentheses around the 27/3 or around the 9/2. Minus 1/3 minus 1/2. And then we want a 6th. There's 4.8. If we wanted this as a fraction, we can go to the math menu and there's a conversion to fraction button. And when we did this, our calculator stored this as answer into its internal memory. And if we just go to here and select convert to fraction, our calculator will automatically do it to whatever's stored in our internal memory. 29/6. I don't know. I think textbooks like fractions because in a sense they're more exact. You don't have rounding error, but also I think in most real world contexts, 4.8 is a lot easier for most people to parse than 29/6. So that's sort of the basic idea of finding area between curves. There's still stuff for us to do. We should probably do a more complicated example if nothing else. But does anybody have questions so far? So you sometimes, if you look at textbook exercises, you sometimes might see something like this. Find the area between f of x is negative 2x plus 5. G of x is x cubed minus 7x squared plus 12x minus 3. You might see a question just framed like that. So what's missing here that was given in the previous two examples? Well, we're going to have to create an integral, an upper minus a lower integral. So we'll have to figure out which of these is the upper and which of these is the lower. What else do we need?
An interval.
I think defined. I think you're getting at this, the technical term being limits of integration, but we're not given an interval that we're working on. Here we were told, we're going from 0 to 3. In a previous problem, we were told we're going from 0 to 1. Here we're just find the area between curves. And this is, you see this, or you see problems framed that way when the curves are enclosing a closed region. And it's obviously slightly sloppy terminology because you can say, well, that's area between the curves, but it's not what they mean when textbooks do that, or internet review sites do that. What they mean is they want the area of the enclosed region. So going back to what we were just doing, in a situation like this, you need limits of integration, and you look at where the region begins. And it begins with these curves hitting each other. And you look at where the region ends. And it ends with those curves hitting each other. And we therefore need those points of intersection. And I mean, going back to what I was saying earlier about using technology to do that, I mean, algebraically, to find the points of intersection, well, points of intersection are where curves are equal to each other. So we set the curves equal to each other, but actually solving this is not at all simple. I mean, what would you even do? You would probably take everything to the right, and then you'd have a cubic polynomial equal to 0. But whether or not you can solve that pen and paper, I mean, you probably can't unless the problem has been specifically set up to let you. So that's why I say I don't want to spend 20 minutes or an hour or whatever messing around with trying to find roots of a cubic polynomial. I just want to take a look at what this region is. I need to graph it anyway, because if I don't, I have no idea what's the upper curve and what's the lower curve. And then when I graph it, I'll also find where the region begins and where it ends. And what I think might happen is that we're going to be in a similar situation to the last problem, where this is going to be multiple regions, and we're going to have multiple intervals. And you see that that is true. There's a region up here, and then there's a region down here. And that's at least set up the integral that represents the area between is. So this first region, let me see if I don't think I can make Desmos highlight this without some hassle, but we see it starts here at 1, ends at 2. You know that a problem has been generated by a textbook if you get these nice integer limits of integration. And on this region here, the cubic is bigger than the linear expression. And then down here, the linear expression is bigger than the cubic. And this region extends until 4. And we have to break this into pieces because there is no single upper curve and lower curve. And I might just set this problem up. I don't know how fascinating it is to watch me type numbers into our calculator, but we're going from 1 to 2 and 2 to 4. And we're going to add these integrals together. And from 1 to 2, the cubic was bigger. Am I right about that? X cubed minus 7x squared plus 12x minus 3, our upper curve, minus our lower curve. And then our lower and upper curves swap from 2 to 4. It's the linear curve, the straight line that's on top. And it's the cubic down below. And then if I were to finish this out, we would take the antiderivatives. We would plug in limits of integration. We would subtract. I mean, does anybody feel a deep need to see this finished out? Okay, yeah. So that's the idea, or that's the main idea between finding area. And again, textbooks maybe tend to want to overcomplicate things. They maybe tend to want to give, super abstruse problems to make sure that students really get it down. I think in general, applications, we talked about the Lorenz curve yesterday, the Gini index. That's something you're going to have to compute with a computer because the Lorenz curve is not a nice thing you can write down. It's something that's just a bunch of data points. So in a lot of real world situations, that's going to be true. And the idea that we have to, man, for just 2 glorious minutes, everything was working great. Let me just sort of briefly touch at least with the 8 or whatever minutes we have remaining on, the, let's see. The idea of using U substitution. I don't think we're going to have time to finish this problem out, but let's say we want the area between these curves. So E goes up very quickly and e to the x squared also goes up very quickly. But you see that this negative sine x is always below this exponential. So this exponential is our upper curve. This negative sine x is our lower curve. If we wanted the area on this interval, it's the integral from 0 to 2 x e to the x squared minus negative the sine of x. And really, the main point I want to make here is something you're going to see probably when you do the U substitution homework, is that a lot of times in situations where you need to do a U substitution, it's also going to be necessary to split the integral up, because what we have here had better be a U substitution, because this is a product of 2 functions and we don't have a product rule for integration. If it's not U substitution, we don't know what to do about it. And this is U substitution. What would a sensible choice of U be here? X squared. du is 2x. That's exactly what we have. Everything's perfect. But of course, then we go over here and we have the sine of x, and there's no way to convert the sine of x into u. So in a problem like this, before you do anything else, you need to use the linearity of integrals. The fact that when you have addition or subtraction inside of an integral, you can split the integral up. And then you're going to have to approach these 2 integrals separately. And for this first integral, I don't think we really have time to finish this out. But for this first integral, we need u substitution. Be careful with these limits. If you just convert to u, you'll need to convert the limits as well. And then for the second integral, we don't need anything fancy. The antiderivative of the negative sign is the positive cosine. So this is something that happens a lot when you use u substitution. We'll see it throughout the course, where you need to use u substitution to resolve part of an integral, but the u substitution won't apply to the whole thing, so the integral has to be broken up. And we'll continue this on Thursday. There's only one thing sort of left to talk about in this section, so it might not be a terribly long lecture, but bright and early at 8 a.m. I will see you.